Welcome to i3TV. I'm Damien Wells and I'm joined today by Peter Gross, Ed Ansett, Luke Neville and Kerr Johnstone of i3 Solutions. We're going to talk about AI and its implications for the data center. I think you would have had to have been asleep for a couple of years to have missed AI, so let's not go into that. We do know that it's going to be very heavy in terms of its resource use of power and its requirement for cooling. But before we get into all that, Peter, how do these GPUs work or operate in a way that's different to the sorts of microprocessors we've seen being used at scale in data centers?
Yeah, it's a very interesting behavior. If you look at the two phases of LLM, and that applies to both inference and training, you have two stages. One is called prompt sampling, where all the GPUs operate in parallel with all the token operate together. And that's very computing intensive. And then on the other hand, you have what is called token sampling, which is primarily done sequential, which is not as power intensive, but it's memory bandwidth very intensive. So essentially, it's a totally different load profile than what we're accustomed. During the prompt processing, the power could there's a burst of demand into the GPUs, sometimes even exceeding the TDP. TDP means thermal design power. But typically, you could see, and there is a variety of each platform has a different behavior. But in general, you could see that the power jumps from a steady state condition, which is maybe 30-40% of provision power, to 80, 90, or 120% of the provision power for it, and that would be for milliseconds or seconds or even longer. And then during the token sampling, the power returns to the previous stage, and it stays there for a bit longer. And you can have this cycling repeating many times a minute or an hour or so. So it's fundamentally different than anything we have seen in the past. And there are some major concerns because it could affect not only the existing distribution system, but could also have an impact on the utilities. When you have this kind of cycling at 200, 300, 400 megawatts, utilities will be impacted. But also, this whole thing has a lot to do with internal impedance. The substation transformer might have a relatively low impedance, but if you look at operation on generators, for instance, it's just an example. With a typical subtransient reactance of maybe 15% or so, it would be highly unlikely the generators can handle this kind of power behavior. So there are interesting things happening here. Obviously, there are things could be improved either through software or through other mitigation methods, including using ultracapacitors, or also using UPSs and increasing the storage on the DC side. So there are ways to do that. But first, I think that the community needs to understand what the issue is before we get more deeper into mitigation.
Okay, well, thank you for that. I mean, I think we can dive into that a bit more in a moment. But I guess the other question that falls out of that is, why do we need such high density racks for AI applications?
Comes back to the same issue for training and inference, for that matter. All the GPUs run in a synchronized mode. They operate like a single GPU. So because of that, the distance between GPUs could be a factor in achieving this synchronous operation. At a certain distance, the delay, the latency, the network latency could be microseconds or so, and that could be significant. So because of that, and the limitation is somewhere in around 50 meters or so. So because of that, you have to have the GPU packed together in close proximity to avoid these kind of latency issues. And that's what's driving these very high densities that, right now you see them hovering around 40 kilowatts per cabinet, but it's going to be very soon at about 70 or so. 100 kilowatts per cabinet is coming. And then the next generation, probably in a couple of years, we're going to see 210 kilowatts per cabinet. And that obviously that imposes a lot of issues, both in terms of power distribution and cooling. And that's another issue that needs to be properly understood, and design issues have to be addressed.
Ed, Luke, you guys have been working on designs for data centers to run AI. How well set are current data centers to actually be able to manage these kind of workloads, based on what Peter said?
The previous generation of data centers, the contemporary data centers, are not well set because for a number of reasons. But firstly, from a resilience point of view. Secondly, and most obviously, from a density point of view. But I'm going to let's just go to cooling first, Luke.
So from a cooling perspective, you can utilize the systems that are deployed in existing data centers to support AI, but obviously you end up with a very inefficient deployment across the facility. So the move that we're tracking at the moment is as Peter mentioned, high capacity cabinets, typically cooled via liquid cooling, direct to chip or direct to plate. However, there's still undefined design parameters associated with these, which seem to be differing from project to project. We would like to drive temperatures as high as possible because it improves efficiency, improves free cooling, removes a vast amount of need for mechanical cooling. And also for countries like Germany, gives you a much better opportunity to export heat to local networks or grids in a useful form, such as above 50-60 degrees can be utilized in many more applications than typical data center heat at the moment, which is sort of 30 to 40 degrees. Even with direct to chip cooling, you still need background cooling. So there's still an advantage for selecting the geography of the data center to suit environmental conditions where free cooling can be provided. And on these facilities, which are large facilities, when you have 15% or 20% ambient loss of the compute load, that still in itself becomes a large central system which does need cooling. And there's obviously advantages to following the lower ambient conditions.
If I may add, data center designs for AI is a very early stage. There are really no mega AI data centers in operation today. There are, but not what we're going to see a couple of years from now. When it comes to design, and when it comes specifically about the cooling, the jury is still out. There are most companies, whether it's hyperscalers or the big colocation players, the big OEMs, the big server manufacturers, they're all still experimenting, looking at various technologies. There are two ways to do that. One is called immersion cooling. The other one is direct to chip or cold plate cooling. Most likely, hyperscalers, the big AI players, will choose to go with some sort of direct to chip cooling for a variety of reasons. And then you have the options of having one phase or two phases which is still debated today. As you probably heard, some of this two-phase refrigerants are what is called PFAS refrigerant, forever chemical. So there are some issues there. That might preclude some of these two-phase refrigerant being used. Whether it's coolant, whether it's the coolant is water or other type of refrigerant is still debated. Whether it's positive pressure or negative pressure, what is the risk of leaks? What I'm trying to say here, there is an enormous amount of uncertainty about the future of cooling. Pretty much everybody agrees that above 70, 75 kilowatts per cabinet air or a hybrid air liquid will not be sufficient anymore, and we're going to have to transition to liquid cooling. So it's the design of the CDU is essential, and that will drive to a certain degree the way this data center will look like.
And then from a power perspective, what we are starting to see at the moment is there's a big drive towards the location of the facility, and that being as close to the power source as possible, i.e. directly adjacent to the substation some instances. And what that's allowing some of our operators to do is to consider the removal of diesel generators to rely upon the grid and the resilience on the grid at that close proximity to source, which results obviously in the removal of those generators. And another aspect of doing that is what we've been hearing today is the cost per megawatt is being driven down considerably. And one of the key factors in trying to drive that cost per megawatt down is to remove some of the resiliency from the electrical network itself, and generators being one of the largest contributing costs to that.
Yeah. So, but I think generally it is a mystery at the moment which way the industry is going to go. I mean, I absolutely feel that it is going to go direct to chip, cold plate, but nonetheless, you've got a big immersion project, haven't you, guys? That's what's the immersion unit rating?
It's 500 kilowatts per tank.
Pretty substantial.
Yeah.
Actual data center or for a Bitcoin, a crypto mining facility?
We don't know what it's going to be used for. We just don't know what the engine. What we believe is going to happen is it's going to be let to basically customers that need LLM and need to develop the model, and then they'll go. They'll lease the facility for a period of time, and then they'll go, and somebody else will come in. It's a bit like co-location, but on an AI scale.
Yeah, the issue here, and that's the most difficult thing for a co-location provider, is exactly what you said, because it's not clear who the user is going to be, and depending on the application, that will drive the density, the types of cooling, whether it's going to be OCP or maybe conventional power distribution, that going to be UPSs or no UPSs. I mean, there are a lot of questions that are difficult to address at this stage, because a big training facility is going to be different than a inference data centers, which is going to be different than a conventional cloud type data centers or enterprise data centers. So all these things ideally should be addressed early on when the customer is identified, and at least the designer has some ideas of what the intention for the utilization of the data center will be.
Yeah, I mean, the ones we're involved with at the moment are, to my knowledge, guys, tell me if I'm wrong, they're all learning facilities, aren't they? They're not inference.
Yeah.
Yeah, and therefore they're located remotely where power is cheap and ideally very sustainable. That's true in one of the cases where basically the power source is almost entirely hydro.
Yeah, that's exactly what Kurt said, right? That the data center is going to go where the power is, as opposed to the older days when the power was going where the data center is. But for training facilities, indeed, the most important thing is availability of power. Latency is not significant. It's not an important factor, so they can be located anywhere. And also the reliability expectations are somewhat lower than your typical inference data centers or cloud data center for that matter.
Yeah, so with inference, the proximity to population is is an issue.
But also, one needs to consider the fact that eventually, I don't know, maybe 5 years down the road, some of these training facilities will be converted to inference data centers. Ultimately, not today, not next year, but ultimately, the power demand from inference data center will dwarf the amount of power required by training facilities, because you have a lot more of them, and it's going to be utilized much more intensively.
Yeah, but do you think the inference data center? I mean, we're talking about smaller scale when compared to learning, aren't we?
Well, it depends. They could be the same scale, but using smaller clusters, smaller platforms, and the fundamental difference between training and inference is that you don't have to have the entire population of GPU servers operating synchronously. So you're going to have smaller clusters of servers performing their function independently from the next one. So ultimately, probably we go way beyond ChatGPT. The federated type AI data centers will be predominant, because eventually every business, every company, every corporation in the world will have their own AI platform, which will reside either into one of the big hyperscalers facilities, like AWS or Google or Microsoft, or is going to be in locating the typical co-location, just like you guys are designing, or it could very well be into a dedicated data center, which could be purposely built, but it's going to be much smaller in size, or it could be a retrofit of an existing data centers, which is also going to be interesting, because you're going to have a relatively large footprint there, with a few cabinets stacked in the corner there, because the density is going to go from 5 kilowatts per cabinet to 100 kilowatts per cabinet. So now you're going to use 1/20th of the space you used before.
Yeah. So, Kurt, from an infrastructure deployment, power infrastructure deployment, what sort of configurations are we doing?
So I think one of the key things from a power infrastructure, and it also touches on the cooling side of things, is the way that we've been designing data centers to date. It's been very much driven by the power in terms of the amount of infrastructure that's required to facilitate the racks. But what we're seeing now is, like Peter and Luke touched on, was a direct to chip. So that almost kind of flips the whole data center design on its head, where you've got substantial amounts of cooling pipework that has to be distributed with a flow and return to each of the racks, which takes up a huge amount of space. So we're having to look at new ways of designing the facility as a whole. So considering flipping everything on its head, where all of the power and cooling is distributed from below, as opposed to overhead like we do with our current data center designs. And one of the reasons for that is what we're finding is, because of the close proximity to the GPUs, like Peter touched on earlier, there's a huge amount of IT infrastructure that needs to go in within the halls themselves to allow that communication between each of the GPUs. So it almost eliminates the usable space within the facility at data hall level itself for that IT equipment only. So we're having to really think about redesigning the data centers from scratch entirely. And then from a power redundancy level, like we touched on earlier, the redundancy is becoming a little less critical than what it is for a typical data center design. So we're now looking at just N distribution to each of the rows of racks, and that redundancy is within the IT infrastructure itself. So a failure of one or two racks or a row of racks isn't as critical as it once was. That load transfer of GPU workload is transferred to the other racks within the same facility.
That's matched with the mechanical infrastructure as well. If you try to deploy what would traditionally be a resilient tier 3 system across these large data centers, the components are unmanageable in their size. So some of the designs we're looking at the moment allows us to break that resilience down onto a row by row basis and deliver that at N with some motive components at N+1. So again, as per the electrical systems, we're reducing resilience across the whole data center as a whole.
A lot of these data centers, primarily the big hyperscaler AI data centers, will operate the version of OCP, and are going to have 48 volt DC distribution to the rack, and that will impose some other consideration, considering how to distribute 100 kilowatts at 48 volts.
Yeah, exactly. Yeah.
It feels like the industry's at a major inflection point. It's probably not since we were deploying mainframes where IBM sort of sold you the computer and sold you the room with the environment to put it in, if you like. Now all of a sudden you've got Nvidia trying to influencing the way that data centers are designed. I heard, incidentally, that they want data centers to be much cooler than I guess we would like if we're going to be able to fully maximize heat reuse. How far is a lack of standards, a lack of experience going to affect the industry, do you imagine, over the next few years?
Inevitably, we're going to go through, the industry is going to have to go through, as it always does, a cycle of learning, right? And evolution. That's absolutely inevitable. And quite how long that take and where it will take us, who knows? I would describe what we're seeing as a divergence rather than an inflection. It's not like the whole industry is going to be doing this. There's going to be plenty of data centers, which I would call them traditional, but they're not going anywhere overnight, and there are going to be more of them deployed. So I think what we're seeing here and what we're talking about here is more of a divergence. It's a new system. It's a new approach. It needs to be considered alongside what we're doing, not as a replacement to it.
Well, yeah, but the problem, the way I see it, is the intensity of the deployment is so high. There is so much being constructed simultaneously at around the world. If you that's going to be a very very fast learning cycle here. Right now, the main priority for every player is to identify location with power and land, relatively inexpensive power that ideally could be green power, have a green component. And there are fewer and fewer locations around the world that can offer this kind of power and land attributes. So it's going to be a very interesting 2 years. After that, whether through SMRs or other type of on-site generation and maybe some new transmission being built. These issues will be addressed, will be resolved. But right now, there is a race, and everybody wants to get these facilities up and running before the competition. So it's a very, very intense period in our industry.
I mean, it's interesting from the point of view that we've been talking about power shortages for quite a long time now, and you say it's going to follow the power. You've got countries or areas like the UAE building nuclear reactors specifically to support these kind of AI loads, making a play as a strategic location for artificial intelligence. Do you think it's going to become more and more, if you like, geopolitically influenced? There's talk about Europe having its own AI.
Most of the AI stuff that we're seeing at the moment is US based that I've heard about. Okay, the stuff that we're involved with, i3, of course, is outside of the US. But you're right. I mean, we had a massive power constraint in the first place, particularly in the traditional markets. Yeah, but just coming back to this, the things that we're doing from an AI perspective at the moment, being LLM based, proximity is not an issue. So therefore, finding the power, you've kind of got out of jail to an extent because of the proximity issue, but you've still got to find the power. And I think for a while that'll be possible, but eventually inevitably, that's going to become more and more constrained as well.
Do you think there's scope for the IT manufacturers to start to think again about the form factors of IT equipment?
Don't be ridiculous. When have they ever done that? When have they ever done that? When have they ever considered us? No, they'll think about it if they need to. If the functionality of the technology, the cost technology dictates it, but it's unlikely to be, as far as I can see anyway, data center constraints. We're going to have to solve them.
If you're going direct to chip, you don't need lots of fans in your server, do you?
Well, it depends, doesn't it? I mean, it depends what you're cooling. If you're cooling just the active components, you still need to cool other components.
But everything else is going to be redesigned. You need to consider the cabinet with this density need to be wider and deeper and higher. It's probably going to go from a standard 600 millimeters to maybe 750 or so. The type of PDU, rack PDUs you use is going to have to be different because it's going to have to use much higher current. The idea is to use higher voltage, also to minimize or reduce the amount of copper use here. And in US, we're going to transition from 12208 to 415 volts, and maybe even a discussion about 575 volts, and then that begs the question about arc flash and what kind of impact that would have into the operation of the data centers. And then there are consideration about weight, because these liquid cabinets are a ton, maybe a ton and a half, and then how you transport the water or refrigerant to the cabinet overhead. What is the danger of leaks there? Or maybe we're going to go back to raised floor, maybe not 2 feet raised floor, but 6 inches or so. I mean, all these are interesting questions that will have to be addressed and optimized as the industry evolves.
Physical space for the compute and the data center is becoming a smaller and smaller part of the overall picture. With some of the facilities we're working on, the data hall's tiny in comparison to the equipment supporting it. So it becomes an easier puzzle to solve.
And on that happy note,
we'll say thank you very much, Peter, Ed, Luke, Kerr. Join us again.